The recent sections gave us the background that we now can look at the essential LTE radio procedures. As in every mobile communication system, also an LTE terminal needs to follow certain steps before it can receive or transmit data. Let's assume we do have an LTE capable terminal as shown here. And guess what? The first thing we need to do is to power up the device. Right after powering up the device, the UE will start with the cell search and cell selection procedure, followed by derivation of system information and execution of the random access procedure. This procedure is summarized and known as LTE initial access. After the initial access procedure, the terminal is able to receive and transmit its user data. Before we now look at each of these steps separately, we need to talk about the physical signals and channels used in a downlink. LTE uses in a downlink two types of signals. Signals which are purely generated in the layer 1, the physical layer. These signals are the primary and secondary synchronization signal, as well as downlink reference signals. Further, LTE uses physical channels which derive the information data to be transported from higher layers, the layer 2 and layer 3. These are, for example, the physical broadcast channel, carrying essential system information, further several control channels, such as physical control format indicator channel, physical downlink control channel, which are required to inform the UE about scheduling decisions. The physical downlink shared channel is used to transport the data, as we will see any kind of data. The obvious transport of user data to the device, but also system information or paging information. Back to the first step after powering up the UE. For the cell search and cell selection, just the downlink physical signals and the physical broadcast channel are important. A successful execution of the cell search and selection procedure, as well as acquiring initial system information, is essential for the UE before taking further steps in communicating with the network. As in wideband CDMA, LTE uses a hierarchical cell search procedure. The LTE radio cell is identified by a cell identity, which one is comparable to the scrambling code which is used to separate between base stations and cells in wideband CDMA. To avoid an expensive and complicated network planning, the number of physical layer cell identities is with 504 sufficiently large. To enable the usage of a hierarchical cell search, these identities are divided into 168 unique physical layer cell identity groups, where each group consists of 3 physical layer identities. A jingle to remember this principle is to think about first names and surnames. The most common English surname is, according to statistics, Smith, which would correspond to physical layer cell identity group number 0, for example. Align the physical layer identity now with the most common first names, for example James, John and Robert. These two types of information are now transmitted using two signals, primary and secondary synchronization signal, where the primary synchronization signal contains the physical layer identity, so the first name, and the secondary synchronization signal contains the physical layer cell identity group, which is, according to our jingle, the surname. Compared to real life, where you use your first name first when you introduce yourself, also the terminal looks first for the primary synchronization signal, then for the secondary one. The computing of the cell's identity based on a modulo 3 operation means multiplying the group identity with 3 and adding the physical layer identity. Let's look at the two signals now. The type of signal which is used for the primary synchronization signal is a Sadov-Chu sequence. Sadov-Chu sequences are Kazakh sequences, where Kazakh stands for constant amplitude zero autocorrelation, where the name describes already the characteristic of those type of sequences. With a constant amplitude, a low peak to average power ratio is achieved, whereas zero autocorrelation means a good time domain behavior. When we look at the constellation diagram of the primary synchronization signal, recorded here with Roder and Schwarz leading signal analyzer FSQ, we will get this result. Can we extract the characteristic of the primary synchronization signal? Yes, we can. The constant amplitude is indicated by the unit circle, The good autocorrelation can be observed by looking at each individual subcarrier carrying the primary synchronization signal. Subcarrier is a good keyword. In the frequency domain, the primary synchronization signal occupies 62 out of 72 reserved subcarriers around the unused DC subcarrier, which corresponds to the carrier frequency in the downlink. The remaining 10 subcarriers, 5 left-hand side and 5 right-hand side, are not used for any transmission. We can call them guard subcarrier. This helps to do match filtering, finding the right sequence used for the primary synchronization signal. As Christina explained, 72 subcarriers translate to 6 resource blocks, as 12 subcarriers are forming a resource block in the frequency domain. With 15 kHz subcarrier spacing, the occupied bandwidth around the carrier frequency is 1.08 MHz. By using the evaluation filter function coming with Rohde & Schwarz FSQ signal analyzer, you can look at each subcarrier individually. For the 3 different physical layer identities, 3 different set of choose sequences have been selected, which have shown the best behavior. The one displayed in the constellation diagram is the sequence for identity number 0. The already mentioned match filtering works generally in that way that the received signal is correlated with the possible sequences for the primary synchronization signal. This procedure is not executed on the received analog RF signal. In fact, this happens in the digital domain. With successful match filtering, the device has identified the used physical layer identity for this cell as well as 5 milliseconds timing. Afterwards, it can execute the next step, looking for the secondary synchronization signal and the physical layer cell identity group to compute the cell's identity. Looking at the constellation diagram showing now the secondary synchronization signal, we believe to see a pure BPSK modulation. In fact, the secondary synchronization signal is represented by an interleaf concatenation of 2 length 31 binary sequences. These 2 sequences are scrambled with a scrambling sequence depending on the physical layer identity, which is transmitted with the primary synchronization signal. So without finding the primary synchronization signal, the terminal cannot conclude on the secondary synchronization signal. The combination of the 2 used sequences defines the physical layer cell identity group. As the primary synchronization signal, the secondary synchronization signal also is transmitted on 62 out of 72 reserved subcarriers around the unused DC subcarrier. That is the frequency domain. So what about the time domain? When we look at the downlink frame structure explained by Christina beforehand, we can see that the synchronization signals are transmitted in the first subframe, subframe number 0, and in the 6th subframe, which is subframe number 5. So the repetition rate for the synchronization signals is 5 milliseconds. The 2 synchronization signals are always transmitted in the first time slot of that subframe, where the primary synchronization signal occupies the last OFDM symbol, and the secondary synchronization signal the symbol before. The determination of the cell's identity enables the UE to examine the pseudo-random sequence used to generate the cell-specific downlink reference signals, as the initialization of the generator based on the cell's identity and the used cyclic prefix, normal or extended. The information which type of cyclic prefix is used in that cell is derived here. The cell-specific reference signals do fulfill 3 tasks. They are used for initial acquisition, current demodulation and detection at the UE, as well as for channel quality measurement. To estimate the channel's quality and to help the UE node B to find a scheduling decision, the network informs the UE via system information about the power level with which one the downlink reference signals are transmitted. The UE is measuring that power level. The difference translates to a so-called channel quality indicator, a CQI value, which is reported back to the network. CQI value stands for a specific modulation scheme, QPSK, 16 QAM or 64 QAM, and which channel coding should be applied to the data. In that matter, the cell-specific downlink reference signal could be seen as a lighthouse, where the power level refers to the height of that lighthouse. In the matter of cell search, the reference signal helped the terminal to get frequency and time-wise fully synchronized. How that can be understood? Reference signals are transmitted as well-defined resource elements. A resource element is the smallest resource unit in LTE and translates to a subcarrier, respectively OFDM symbol. In the frequency domain, every sixth subcarrier carries a reference symbol out of the generated reference signal pattern. In the time domain, the spacing is 4 OFDM symbols as shown in the diagram. Thus, the resource block, which is 12 subcarriers, 7 OFDM symbols, when normal cyclic prefix is used, 6 OFDM symbols for extended cyclic prefix, contains 4 reference symbols at certain resource elements. LTE uses MIMO technology. 1, 2 or 4 antennas are used for transmission or reception. Depending on the MIMO mode, here special multiplexing, different data streams might be transmitted over the antennas. To ensure correct demodulation and decoding at the terminal side, the UE needs to distinguish between the different antennas. This is done with the help of the reference signals. As you can see in our example with the 2 antennas, the second antenna issues their reference signal pattern at other resource elements than the first antenna. The frequency and time domain spacing stays the same with 6 subcarriers and 4 OFDM symbols, but where the first antenna would issue their reference signal pattern, the second antenna would not transmit anything and vice versa. This is indicated by the hashed resource elements in the graph. With the help of the reference signals, the UE gets fully synchronized to the radio cell. After that, the UE looks for the physical broadcast channel, which carries the master information block. The physical broadcast channel is, as all control channel in Downlink, QPSK modulated. Prior to modulation, the channel is scrambled with a cell-specific scrambling sequence. In contrast to the synchronization signals, the physical broadcast channel is transmitted on the 72 subcarriers around the unused DC subcarrier. In the master information block, the UE finds the information which system bandwidth is used in the cell. 1.4, 3, 5, 10, 15 or 20 MHz. The system frame number, as well as the configuration of a specific downlink channel. Further, the UE gets the information how many transmission antennas are used in that cell. And this is all what the UE knows after successful execution of cell search and cell selection procedure. Further information are required to execute random access procedure and to enter the network. Let's see how system information are distributed in LTE.
Andreas, I have a question. You explained that the repetition rate for the synchronization signals is 5 milliseconds, so every 5th subframe. What about the physical broadcast channel?
Yeah, sure, good question. The physical broadcast channel and so the master information block has a transmission time interval of 40 milliseconds and can be found in every radio frame. But of course you need to decode the 40 milliseconds to get the whole information. The data in the master information block are the only system information which are transmitted via a dedicated control channel, means the physical broadcast channel. All other system information are transmitted using the shared channel principle. That is what Christina explained during explanation of channel mapping in LTE. At that stage we learned that the logical broadcast channel can be either mapped to the broadcast channel or the downlink shared channel as transport channel. The BCH is then mapped to the physical broadcast channel, where the downlink shared channel is mapped to the physical downlink shared channel. So all other system information than the master information block are mapped to the downlink shared channel, which is a fundamental difference to 3G mobile communication systems. Nevertheless, also in LTE, system information that logically belong to each other are summarized in system information blocks. Further system information blocks with the same timing requirement can be grouped into so-called system information messages. First of all, the UE needs to find scheduling information for those system information, which is provided by the system information block type 1. This one is already transmitted using the shared channel transmission principle and has a repetition rate of 80 milliseconds. With information out of the system information block type 1, the UE would be able to check the periodicity for system information messages. There could be up to 32 messages. A message contains system information blocks with the same scheduling requirements. The system information block type 2 is the one the UE is now looking for, as this one contains information about the common and shared channel usage and therefore information how to perform random access. System information block type 2 includes information about the random access channel, which is the transport channel, and the physical random access channel, which is the physical channel where the PRACH is mounted to. Timing is the one side of the medal. The other side, which resource blocks, so which part of the spectrum now carries the system information message, and therefore the system information block. We will later on talk a little bit more in detail about this, but as Christina already highlighted during explanation of the downlink frame structure, the first symbols of each subframe contains the physical downlink control channel, PDCCH, and this one informs all the UEs about scheduling decision, and beside this, on which resource block system information can be found. A specific identity is used on the PDCCH to address system information to the UE. This is the System Information Radio Network Temporary Identifier, which is defined by 3GPP, the standardization body, and is therefore known by all UEs. With decoding the right resource blocks, the UE received the information how to use the random access channel and how to access the physical random access channel and can perform the random access procedure. The random access procedure contains several steps. First of all, a knock-knock. The random access preamble is sent by the UE, which means hello network, here I am. The preamble itself is a set of choose sequence which is sent on the physical random access channel. 6 adjacent resource blocks out of the available bandwidth are occupied by the preamble, but where these resource blocks are located is configured by higher layers via the system information. Based on information derived from system information block type 2, the UE also knows in which subframe a specific one or all in that radio frame the preamble can be transmitted and which preamble format to be used. At all there are 5 formats, where the first 4 are applicable for LTE FDD and LTE TDD, and the 5th one just for LTE TDD. The different formats are necessary to bridge the gap between the base station and the UE. After the UE has sent the preamble, it waits for a response from the network. If no response is received, the UE increases the power level with which one the preamble was sent. If the E node B has received the random access preamble sent by the UE, the random access response comes on the physical downlink shared channel. This response includes uplink timing adjustments, instructions, an initial uplink resource grant required for transmission in step number 3, and an assignment of a temporary identity. In the next step, the step number 3, the UE first time uses the physical uplink shared channel. The transmitted information includes, for example, a radio resource control connection request, tracking area update, or scheduling request. It also includes the allocated identity. Step number 4 marks the contention resolution. The random access procedure can be verified using Rode and Schwarz CMW 500 LTE protocol tester step by step or as a complete procedure. The instrument is ready, and so testing depends completely on the implementation status of the device under test. With passing the random access procedure, the UE is known by the network and would be able to transmit and or receive data. We know already that data in LTE, it doesn't matter if it is system or paging information, so control data or user data, is transmitted via the physical downlink shared channel. As the name implies, this channel is shared between all the UEs in the radio cell. And particular UE is interested to know if it is addressed with data and where to find this data. Another UE is looking for the radio resource blocks carrying system information, and so on. The device needs to be informed about the scheduling decisions, and therefore all devices need to read the physical downlink control channel. This channel is transmitted over the entire bandwidth in the beginning of each subframe. Via unique identities, information are provided to the UEs if they are addressed with data and where to look at on the physical downlink shared channel. But of course there might be more than one UE in a radio cell, and all of them needs to be addressed with control information once in a while. Therefore the amount of resources means how many OFDM symbols in the beginning of a subframe are occupied by the physical downlink control channel might differ. The UE needs to be informed about that. This information is provided to the UE by another channel, the so-called Physical Control Format Indicator channel. This channel, transmitted on defined resource elements on the first symbol of each subframe, contains the information how many OFDM symbols are used for the physical downlink control channel. Depending on the bandwidth used in this cell, the number of symbols differs. In case of a 10 MHz channel, respectively 50 resource blocks, at minimum 2 OFDM symbols are used in the beginning of each subframe, at maximum 3. 4 OFDM symbols are reserved for future use. The hybrid automatic repeat and request for LTE in the downlink works the same way as for HSDPA. The UE can request the retransmission of incorrect received data packets via ACNAC reporting. The ACNAC information is sent in the uplink on the physical uplink control channel, PUCCH, or the physical uplink shared channel, PUSCH. This depends if in parallel uplink data transmission is ongoing or not. The ACNAC sent in the uplink refers to the data packet received 4 subframes, means 4 milliseconds earlier in the downlink. This is a timing relation in LTE FDD. In TD-LTE it is a little bit different. Here the timing relation depends on the uplink-downlink configuration, means how many subframes are allocated for downlink transmission, how many subframes are allocated for uplink transmission. Because of that, a single ACNAC response for providing HARC feedback could be used in TD-LTE for multiple PDSCH transmissions. As we learned, Evolved Packet System, EPS, is efficiently a connection-oriented transmission network, and as such, it requires the establishment of a virtual connection between the UE and core network, respectively Packet Data Network Gateway, before any traffic can be sent between the UE and the network. This virtual connection is called a EPS bearer, a term that emphasizes the fact that this virtual connection provides a bearer service, means a transport service with specific quality of service attributes. The EPS bearer corresponds to the PDP context used in GPRS wideband CDMA. The EPS bearer has to cross multiple interfaces to establish that connection. Between the UE and the eNode B, between the eNode B and the serving gateway via the S1 interface, and between the serving gateway and the packet gateway. A lot of procedures have to be executed and a lot of information are exchanged between network and the UE. As shown, tasks like the initial access procedure have to be passed first, further RRC connection establishment, attach request and PDN connectivity request, authentication and non-access stratum security procedure, checking the UE capabilities, access stratum security, RRC connection reconfiguration, attach accept default EPS bearer context request, and as a last step the default EPS bearer context accept.